for the invitation to organize this meeting. And I'm happy to talk about my favorite topic, which is geometry and combinatory. So, and again, it's a joint work with my colleague, Mr. Now, so I mainly will talk about extremal hypergraphs actually. So we can jump from here. Let's start with the problem. This problem was proposed by Kandikov, Erdős and Guy, and it is a typical problem what Erdős used to propose, that very simple to state. So the question is that given an endpoint set on the plane, and this endpoint set determines at most n choose 3. And suppose that there are no 3 on a line. I mean, endpoints are regular in general position. Now, so we have n choose 3 triples. We just measure the angles, and we call triangle almost regular if the angles are between 59 and 61. So they don't differ too much from 60 degrees. And it's a commutator problem. For every n, we got an integer here, the maximum number. You consider all possible combinations. And actually, they proved an upper bound, which is not that far from the truth. 1/3 times n choose 3. So it's not possible that all the triangles are about regular. And it's obvious that the answer will be n cubed, because we put our points, so we need a construction now. We consider this is a regular triangle. Well, it's not completely regular, but we put n over 3 points in each group, very close to each other, to a vertex of around the vertex of a regular triangle, and then obviously every angle will be very close. Well, if it were a regular, ABC would be a regular triangle. So it is clear that the answer is n cubed, and the question is only the coefficient. What percentage of triangles could be almost regular? So that's the problem. And actually, we can make a slightly better construction. We can repeat. So these groups are extremely small because we want the angles. So we want these angles about the same. So I just enlarged for easier understanding. So we just repeat. So we have n points we want to place on the plane. We split them into 3 parts, and we got a recurrence. Where f of a is this h of a. So fortunately we can add this up, and it gives something n cubed over 24, which is 1/4, 25% of the triangles. And also, actually, we can do this for any shape. But before I do this, I let state the theorem we have, that indeed the answer is exactly what was conjectured, is n cubed over 24. So if we have so in human language, this formula says that if we have n points on the plane, no line, then the maximum number of triangles determined by these points which are almost regular, where the angles are differ by at most 1 degree from the 60, 60, 60, is 25% possible triples. And actually we have an exact formula. So exactly that kind of configuration, it's one of the extreme configurations. There are some slight differences. Now, so this is our main result here. But what I would like to talk is not exactly this one, but because here we did this with geometry. But instead, I would like to talk about the method, which is a very powerful method. Let's generalize the problem first. Two finite sets on the plane are called epsilon similar if the distance is about the same. More exactly, there is a bijection between the points A1, B1, B2, B2, and there is a ratio, of course, such a way that the distances are about the same. So, of course, we will think that epsilon is very small, like 1% or less. So 2 point sets are similar if the distances are, well, it's slightly distorted. And we can ask in more general, not like what Conway, Croft, and Erdős and Guy did, we can ask for any triangular or any finite shape A, what is the maximum, and for any shape, any number of vertices, and any little epsilon, we can ask how many epsilon similar copies we can have, how many we can push. Again, if we split the endpoints in, to make a construction, we just enlarge the shape very slightly. So we have one copy and we put n over k points around each vertex. Then we have a natural easy flower bond, which is n to the k, where k is the size of the set. And if we iterate, we got a slightly bigger coefficient. And obviously n choose k is an upper bound. So the order of magnitude is not a question here. Now we mainly consider triangles, but just to show that one has to be careful if our triangle comes from the regular pentagon, and we can do the same procedure with the vertices of the regular pentagon, just putting groups of points n over 5 around each vertex, and then iterate this construction, putting n over 25 points in each group to another pentagonal shape. Now, this configuration will be full of, I don't know how to call this triangle, 72, 72, 36 degree, plus minus epsilon, of course. We have a slightly different recurrence, but it gives the same answer, actually. Thank you, as before. And probably this is the best. We cannot solve this case. Yeah, that's the exception. So the answer definitely will depend on the shape. Although, well, the answer here is the same, but the different configuration, different construction, different hypergraph, different hypersystem, what we got. And also, if we take any orthogonal triangles, it should not be isosceles, it's just orthogonal, then we can place even more, because we have 4 groups around the 4 vertices of a rectangle. Of course, a rectangle of the what we need. So what is the right triangle? So given the sides A, B, and C, shapes, the shape of the triangle, and then we can start with 4 groups. Obviously, it's much denser, because even in the first step, we immediately have 4 triangles in 4 elements. And that gives again some constant tensor cube, but now it's a much larger constant. And one more example of this type, when we have another well-known triangle, what we got from the regular, by cutting into 3 identical parts, the regular triangle, then we have a different occurrence relation here. It's kind of symmetric, but into the center point, the center group rather, we can put more points. Then we got a slightly higher density. It's an irrational number, some root of a third degree polynomial what we obtain, and I conjecture that this is the best, but we cannot prove. Now, because now, so what can we do? We need a definition first. We call a triangle atypical if there are small integer coefficients. Well, the triangle is given by the sides or the angles. Of course, alpha plus beta plus gamma is just pi. So given the triangle, and we call it atypical, more exactly k atypical, where k is an integer. If there is a linear combination, or an integer linear combination, which is non-trivial. Okay? The trivial one, what we learned in school, alpha plus beta plus gamma minus pi is 0. So the coefficients are just 1 and minus 2, negative 1. So, but every other linear combination, well, just like 2 gamma is pi, that means orthogonal triangle, or some other linear combination. Those which we call atypical, because if we have just a triangle alpha, beta, gamma, 3 angles, usually there is no any integer linear combination, well, except the trivial one. Now, instead of this definition, actually what we really need is a more general one. It doesn't seem to be immediate. This is not the same k, it's a bigger k. Because if we have a linear combination like that, we can write it down this with the cosines. You know, the cosine is a rational polynomial of the sides A, B, and C. So we can have a rational polynomial. So if you have a linear combination like this, then we also have a rational polynomial with variables of the 3 sides, A, B, and C, with small integer coefficients. So that's what we really use. So we call it atypical of degree k. If we have a polynomial with small integer coefficients, which is not a 0 polynomial, obviously, non-vanishing polynomial, and so something like this. So I hope you recognize that this is the orthogonal triangle. This is the isosceles triangle. So those are atypical triangles. Everything we learn about in school, those were atypical triangles. So typical triangles have no polynomial relation between the sides, among the sides. Now, well, there are many. So our aim, what we actually eventually proved, was that almost all triangles are typical, and for almost all triangles, the answer for the Cornway-Croft-Erdős question will be 25%. And I would like to show a method which we tried hard, but eventually we needed a different method to finish. But anyway, so our main result is that apart from the atypical triangles, the answer is always n cubed over 24. So for every triangular shape, we have a small epsilon that we cannot have more than 25% among an endpoint set. Now, before, I don't know how much time I have, I'm sorry. I don't know. I don't have. Can you please ask how much time? So, how much time I have? Sorry.
How much time?
Yeah, okay. Maybe
20 minutes.
20 minutes. Okay, then.
A lot of time. Oh, yeah.
Sorry. But anyway.
Sorry, you had K atypical, not just atypical.
A K atypical, yeah. So we have a bound, yeah.
So you have the bound or not?
Yeah, we have bound. So, before I start with the hypergraph tools, hypergraph problems for triple systems, I want to mention that actually, if you want to do homothetic copies, then we got a completely different problem, which also has a long history, and it's actually real mathematics, much more serious mathematics. So this also fits into our terminology when epsilon is 0. So we want truly homothetic copies. Then for any endpoint set, we cannot have more than n squared, because 2 points will determine the shape. Okay, so 2 points fixed, then we cannot fit there in too many ways. So the n square upper bound is for every finite a. It holds for every finite a, and Elekes and Erdős proved that actually this n square is not that bad bound. So for every shape, they have a bound which is almost n square. Have a construction. Of course, it's a clever algebraic construction. And for triangle, they have indeed n square. And a couple of years later, Laskovich and Ruzha solved the problem where, so what is this statement? So given a configuration A, now it has more than 3 points. Because for 3 points, the order of magnitude is always n square. It's difficult to imagine, but it can be done. So, and they asked which shapes have which shapes we can have a construction that we can put n square points, n square copies, homothetic copies, and which shapes not. And the answer, actually, this is what came to my mind first immediately. Well, not really the joke. So it's So the cross ratio should be algebraic. The cross ratio of 4 points is written here. So we consider the 4 points as complex numbers on the complex, not plane, but complex line, so on C. So we consider the 4 points as complex numbers. And this is the ratio of 3 points, ratio of the other 3 points, and we take the ratio of those two. That's the cross ratio. And if this cross ratio is an algebraic number for every 4 points, then they have a construction C times n squared. If it's not algebraic, then they were able to prove it's little n squared. So it's, it's a beautiful result. And actually it's a very short paper. I mean, they use the right tools, of course. Well, there are many related results, and of course we can extend the higher dimension. Anyway, the truly homothetic copies, that's a kind of algebraic problem, rather. And there are beautiful. I wanted to mention these two beautiful results here. Erekes and Erdős and classical solution. Now, let's return our approximated result. And let's talk about the proof, more exactly the method. So the method is I'm going to use Turan theory. We're already familiar from, if not else, that Miki Simonovic lecture, the Turan number of a class of graphs is the largest number of edges without some forbidden configurations. So this is what we all know, that if you have a triangle-free graph, it can't have more than n squared over 4 edges. So this is a typical result, and this was the first result of this type, one of the first results. So this is what we are going to use for combinatorial geometric problems. We also familiar with Turan theorem that is solved. That's why it's called Turan type problems. If there is no, you see, I stole this picture from Wiki. So this is a 3-partite complete graph, and obviously there is no K4 in it, and that's the largest. So that's how we remember. Now, how we can use the Turan's theorem for geometry, combinatorial geometry problems? Here is a very simple example. Given n points, and we just count how many segments have distance about 1. Distance between 1 minus epsilon, not plus epsilon. And the solution here is almost trivial using Turan's theory, because given the point set, given the epsilon, which is small, we construct a graph. Those are the pairs where the distance is about 1. And we just consider the graph after that. We just check the properties of this graph, and we observe that this graph can have a regular a triangle, but they cannot have a K4. So we cannot have 4 points on the plane. So we need very little geometry. We cannot have 4 points on the plane that all the distances are about 1. All the 6 distances. So K4 is forbidden. So we got immediately an upper bound for our function, what we are looking for, that the Turan number for K4 is an upper bound. And that's the best. So we can do that with 3 groups. So that was an easy application. I want to show you another one, which is also an easy application, but that was one of the first by Paul Erdős, the unit distance problem. So S of n is the maximum number of unit distances in endpoints on the plane. Now, again, we do the same as before. Given we want an upper bound, so here we just give an upper bound. So we have endpoints on the plane. Consider the unit distances among the pairs points. That define. We got a graph. This is the definition of a graph. Certain pairs, and this unit distance graph. Erdős observed immediately that there is no K23 in it. There is no complete bipartite graph on 2 plus 3 vertices, which is an easy elementary geometry. So if we 2 points, this is a 2-point side somewhere, then there is 1 point on the orthogonal bisector here, y1, y2, and there is no place for y3, so they should coincide or something. So we cannot represent the unit distances K23. So the unit distance graph has no K23, so the Turan number for that graph is an upper bound. And the Turan number for this complete bipartite graph K23 happens to be n to the 3/2, so he got immediately n to the 3/2 upper bound. It's still unsolved what is the true order of magnitude of that. Now, this is the kind of method we would like to use. But instead of graphs, we will have triple systems. So it is not unheard of. There are many applications. But anyway, we will talk about triple systems. And one conjecture is still unsolved. Turan. One conjecture is, what about if we are looking for a complete triple system of 4 vertices? How many triples we can have? How many 3-element sets we can have? And he has a construction, it's kind of here, which has 55%, 5/9 of all the triples, without a K4. And he conjectures that this is the best, and there are plenty of results. And on this topic, the best upper bound is due to Raskolov, who managed to prove an upper bound because we have already a lower bound, as you can see the construction. So managed to prove an upper bound which is 1% close to the lower bound, which is pretty good. And another configuration, what we will use later, is the K4 minus. When we are looking for a K4 minus, this is only 3 triples and 4 elements. That's not all the 4 triples, only 3. That's why I call it K4 minus. So, here the conjecture is that the best ratio is 2/7. And again, the best bound was proved by Rasborov's method, a computer-assisted proof. The 2 sets of people proved, Emil Vaughan and about the same time. But still it's unsolved. So, well, immediately, what we have conjectures by Erdős and Sós, short conjecture, So what is our method? Maybe I jump there. So given a point set, you already had a lower bound which gave 25% of the triples, 25% of the triangles, epsilon similar to the given triangle A. Now, we need an upper bound. How to make an upper bound? Just like in the unit distance problem, given the point set, we make a hypergraph. Well, those triples which are epsilon similar to A. That's a triple system. And now we are looking for forbidden configurations. So we can make a little lemma, little geometry statements like this one here. So if the triangle is not orthogonal, not the triangle from the regular triangle, not, well, there's one more case. If none of these, so it's a typical triangle, then we cannot put 3 copies on 4 points. So at most 2 copies only. So K4 minus is a forbidden in our hypergraph. So this is a good observation because it immediately gives an upper bound using Turan's theory. But this upper bound cannot be 0.25 because we know that this Turan number is larger than 1/4, as you see. But it's still a good try. We got pretty close to 1/4. We need more excluded configurations if you want to use this method. We can have a lemma like this that, for example, a 5 wheel, what I denote by C5 plus. This is an atypical, I mean, we cannot make 5, well, here, these 5 triangles are similar to each other, but these are orthogonal triangles. So for any orthogonal triangle, I can make a 5 wheel, represent it as a 5 wheel. So I take the triangle is orthogonal, I just translate, I got another one, and the third one comes automatically here. And then, because this is these 3 points on a line, I can put here a somewhat larger similar shape. So that's a 5 wheel. But whenever I have a 5 wheel of the same triangle, and from the center point, I add up the angles. The sum of the angles should be 2 pi, or maybe 0, because I can go back and forth. But anyway, it should be 0 modulo 2 pi. So we got, well, I just wrote down all the possible linear combinations, what we got from the angles. So if we exclude those triangles, then in our hypergraph, we can't have a 5 wheel. So we have an upper bound immediately, the Turan number of the 5 wheel for our original geometry problem. And actually, well, the little work, we can make more excluded configurations. You see this was the K4 minus, the first one, here the 5 wheel. It's a different numbering now. But we can have other small configurations. Of course, it's a little work to do that all the 9 are forbidden. But it's not that hard either. And then we can use that, okay, take a triangle which cannot represent any of these 9. Then with a small epsilon from the hypergraph of the triple system, the similar triangles, almost similar triangles, the hypergraph of almost similar triangles, all the 9 will be forbidden. So we need this Turan number. And I am pretty sure that it's n cube over 24. we could not prove in this way. We used the phlegmatics. We asked our friend who is and what this computer gave back only 25.07, which is very close to 1/4, but you know, in mathematics it's not 1/4, so it's 25.07 is not 1/4. So eventually, although I am pretty sure that this two round number is 1/4 times n choose 3, actually there's a conjecture that if we exclude the first two, that already gives 1/4. It's not my conjecture, it's a conjecture by Emil Wong and Vargas. Now, we have plenty of more things how we proceeded in geometry, but what I really wanted to show you, well, it was an unsuccessful attempt, anyway, so whenever we see a kind of commutator problem like this, then we can try to run type hypergraph results, and sometimes we succeed, sometimes here we didn't, so we needed other ideas to finish, but that will be another time. So maybe at the finish I just show that so I still have plenty of beautiful pictures computer generated. So these are 5 wheels or 5 circles. Here, this is one 5 wheel, another one. You see here it goes back and forth. So these are 5 triangles, all the same shape. So there are some exceptional configurations, but otherwise for typical triangle, we managed to have a result of this 25%, but it will be presented another time. So thanks for your.
Okay, thank you very much. Questions? Comments?
The general problem, what bounds do you have on the other side?
For almost all triangles we have 1/4.
But for the general case,
For general case, a larger configuration. Well,
I'm sure you have some.
you cannot. Yeah, no, we didn't even try.
You didn't.
Any more questions? No? Okay, let us tell the speaker once again. And we have 5 minutes break.